the Kiel University, and he will talk about quantum harmonic analysis for polyanalytic Fock space. Please, Raffael.
Thank you very much for inviting me once again to your Toeplitz seminar. So today my talk will be two parts. So first, I will talk a little bit about quantum harmonic analysis, some general theory, tell you what it is and what it can do. And alongside, I will always have the standard Fock space you're probably familiar with, and alongside, because it's a little bit easier to explain everything than explaining it directly on a polyanalytic Fock space. But then in the second part, I will show some applications to polyanalytic Fock spaces and show you some new results that we found together with Robert Fulcher. And in case you're really interested, there is also an archive preprint under the same name. You can find everything I'm going to tell you today there as well. Okay, so let's start with some quantum harmonic analysis. So what we need here is a symplectic vector space, and to make it very simple, let's just take R2 with the standard symplectic form here. So we identify R2 with a complex number, and then the symplectic form can be written in this very simple form.
Well, why do you put multiple 2? It's
don't worry.
Many uses just imaginary part of Z.
Yes. Yes. I will tell you in a second why the 2. Don't worry about it right now. Yes, there is a 2, and it will be clear later why there is a 2.
Yeah, you know, when you write composition of the while operators, you divide by 2.
Yes, that's exactly the reason. You see it down here. Okay. Right. So now what I want to do is I want to take a so-called sigma representation of the translation group of my complex numbers. So that's a unitary representation. So it's a map into the unitary operators on some Hilbert space, let's say separable one. And I want it to be irreducible. That is, there should be no invariant subspace. And well, I say here sigma representation and not just representation because, well, we have this additional unimodular factor here. So that's why I call it a sigma representation. It's not exactly a representation, but almost up to this factor. And I also want it to be strongly continuous. So it should be continuous with respect to the strong operator topology on the unitaries, right? And as Nikolai said, since there is a divided by 2 here, I put a 2 in the symplectic form so that it gets canceled. That makes it a little bit easier. But in principle, you can take any symplectic vector space here, and you could take any symplectic form, and the quantum harmonic analysis will work.
Because, so, you know, according to me, because better without 2, because geometrically it would be area of parallelogram.
Yeah, that's true.
On ZW.
Yeah, that's true. But well, then you have to change the measure on the Fock space to make everything work. But okay, so right, the standard example is, as I said, the Fock space. So that's the square integrable functions with respect to this Gaussian measures. So the entire functions in there. That's the Hilbert space, of course, as you all know. And there you can write down this representation very easily. And these are usually called the while operators. So they are just shifting the function, and then you have to account for the measure. And then you have an additional factor here to make this unitary. These are the normalized reproducing kernels of this Hilbert space. And well, it can be written explicitly as this is exponential. So that's sort of the standard example. You can check easily that everything here is satisfied. Okay, now why quantum harmonic analysis? So the idea is you have some very strong tools from harmonic analysis like convolutions, Fourier transform, and so on. And we want these tools for harmonic analysis. And it will be clear later on why this is very useful. So what quantum means here is, well, quantum usually just means you replace functions by operators, right? And so what we need to do is we need to, in order to define, for example, a convolution, well, if you think of a convolution, what do you need? Well, you need to know how to shift a function. So on the operator side, you need to know how to shift an operator. And that works like this. So on the function side, you just have a shift, and that's the corresponding thing on the operator side. So you put your while operators from left and from the right. So this is, in fact, the inverse of this one, and this then acts as a shift on your operators. We'll also need a reflection. So the Stone von Neumann theorem guarantees such a reflection that satisfies this identity here, well, then you can define a reflection essentially in the same way as you defined the shift. So reflecting on the function side is just, well, reflecting the argument, and on the operator side you would just put your reflection on both sides of the operator here. Of course, the inverse of the reflection here is the reflection itself. That's why you have the same thing here on both sides. Okay, and now you have everything ready to define a convolution. We just do this by analogy, really. So if you think of the usual convolution of functions, that's just the usual formula for a convolution. And now let's just, for starters, replace this g here, this function g, by an operator. Okay, so what you do, well, we have the function f, that's the same, and then, well, g is replaced by operator, but it's not g, but it's a shifted version of g, so we need to replace it by a shifted a, right? And then you get this Bochner type integral here. Of course, you have to think a little bit about, well, when does this actually converge, right? As well on this side, of course. So for regular convolutions, well, you know, you can choose one function to be, for example, L1 and the other one L infinity, and then you will end up in L infinity and so on. And you have this Young inequality, and we'll get back to that. So on the operator side, well, you have to do essentially the same thing. So you have to take either an L1 function and a bounded linear operator, then this is well defined, or you take a bounded function and then you have to take a trace class operator. So you see on the operator side, L1 is always replaced by trace class, L2 will be replaced by Hilbert-Schmidt, and L infinity will be replaced just by the whole set of bounded linear operators. And essentially you could also replace LP by the Schatten classes and so on, but we won't need them today. We just need L1, L2, and L infinity today. Okay, so again, you need one of the two. You need to be in L1, the other one in L infinity. If you have an operator, well, that means the operator has to be trace class if the function is in L infinity, or here vice versa, and then this converges at least in the weak operator topology. So this makes sense. But we can also define an operator-operator convolution. So when we replace both of the arguments by operators, and now we have to work a little bit more, but again, a standard technique is to replace the integral by the trace. Right, so now the integral is replaced by the trace, and well, then for the second argument again we put in the shift, but now we also have this reflection in there. That's not immediately clear why you would do that. Like if you go by analogy, you would maybe don't see why you want the U here. But the reason for that is just that, well, the trace is cyclic, you know, and when when you cycle everything through, you see that you need these U in order to make this convolution commutative. That's the only reason. So if you commute everything through, and well, you want the B on where the A is and the A where the B is, and then if you don't put the U, then you get the same thing, but with minus C, and that's why you have to put this U as well, and then this will be commutative.
So you mean that A convolution with B equal B convolution with A?
Yes, exactly.
F convolution with A, what is A convolution with F?
By definition, it's the same thing.
The same thing. Okay.
But just by definition, you define it to be that way. And we won't need it, really. Right, and again, of course, you have to make sure that this makes sense. So at least one of these operators should be trace class, then the whole thing is trace class, and thus the trace actually makes sense. Okay, let's look at an example. How does this work? So I have to take, let's consider the operator convolution first. I have to take one operator that can just be a bounded operator, and the other one needs to be trace class. And I take a very simple one. That's just a projection onto the constants. So this tensor notation means just that. So you take an inner product with the second argument, and then you multiply with the first argument. So that's a rank 1 operator. In particular, it's trace class. And let's see what happens if we.
So basically, it's a projection onto the one-dimensional space generated by identity.
By the one function, yes.
Yes.
By the function constant equal to 1. Yes.
Yeah.
Yes. So yeah, let's just apply the definition of this convolution. So that's just the definition I put in. So projection here, that's this 1 tensor 1 here. And then, well, from the left, we can just, by the definition of this tensor product, we can just put in here. And, well, if you come from the right, you need to put in the adjoint, right? So that's why you get WZ times U here, because you put that inside on the second argument here. And well, now you can just compute, right? So the U does nothing, that's just a reflection, but if you reflect the one function, that does nothing. And then if you apply the while operator to the one function, well, you can see here immediately, well, just the KZ remains, right? And here the same, so we get this. And now the trace of a rank 1 operator is just the inner product. So you get exactly this. And this is the thing you all know, right? That's the Bayesian transform. Okay, so this tells you, well, if we take an arbitrary bounded linear operator, I convolve it with this projection, then we get the Bayesian transform of A. Okay, so that already tells you this convolution is somehow useful, because we can get one of the most important things in operator theory, or in the theory of Toeplitz operators. The Bayesian transform this way. Okay, let's also look at the function operator convolution. That's the other one. So now I just take a bounded linear function, and not a bounded linear function, sorry, a bounded function, and I convolve it with the same operator as before. I put it into the definition. Now, you see, I have to consider this in the weak sense, because I told you this integral is to be interpreted in the weak operator topology. So I have to take something here and, well, some functions here, and why not just take the normalized reproducing kernels, because, well, that will give me the Bayesian transform. And once I know what the Bayesian transform is, I know what the operator is, because the Bayesian transform is injected. Okay, so I need to put something there, and, well, let's just take the Bayesian transform there. Right, okay, I put it into the definition. We get this, again, we use some standard properties, how the while operators interact with the normalized reproducing kernels. And you compute, well, you use the definition of this tensor product, you get this simple thing, you can compute this, and you get an exponential. So this is really just straightforward computation here. And you see this here is exactly the Berzin transform of F, or the heat transform if you want. So it's F, the convolution of F with the heat kernel, except for this pi. So this tells you the Berzin transform of this operator is the Berzin transform of F, or in other words, the Berzin transform of the Toeplitz operator with symbol F, right? So this tells you this is really a Toeplitz operator. Okay, so you see, if you convolve an operator with this projection, you get the Berzin transform. If you convolve a function with this operator, you get Toeplitz operators. Okay, so you see this comes in really naturally into the theory. And in fact, what we've just shown here is that, so I took the Berzin transform, and on the previous slide, I showed you that, well, Berzin transform is just the same as convolving with this projection. And we've shown, well, this results in pi times the Berzin transform of F, which is just F convolved with this exponential, with this Gaussian. And, well, I didn't show you, but it's easy to check that the convolution of P with itself is just exactly this exponential. So we showed some sort of associativity here, right? So we can compute this first, or we can compute this first, and we get the same thing. And this actually works much more generally. So in fact, we have associativity with this convolution, which is of course nice because you have this with convolutions of functions, of course. But what's remarkable here is that these stars are actually not always the same operator, right? So I always put a star here for convolution, but it's not always the same operation. You see here on the left, we first do a function operator convolution that gives you an operator, and then operator convolution. But on the right, we first do an operator convolution, and then this gives a function, and then we have a function convolution. So this star is not the same as this star here. Right, so this is kind of remarkable, but everything works out, and therefore we don't have to worry about which star is which and so on. We can just use the same thing. It's really convenient. And in fact, this works generally not just in this example with this very special operator, but it works very generally. You can always compute these convolutions in any order you want. Then you also have the Young inequalities to estimate your results. So if you convolve a function with an operator, you can estimate this by the infinity norm of F times the trace norm of A. You have a pi here you would maybe not expect usually in the inequality, but well, this comes from some wrong normalization that, well, someone wrongly normalized something, and then, well, after some time you cannot change the definitions anymore, and then where it gets some constant here you maybe don't want. But let's not worry about this. Of course, it also works the other way around. So if F is in L1, you also get the other inequality. So the L1 norm of F times the operator norm of A also works. So I didn't write it down here, but the other way around it also works. And the same here for the operator convolution. The infinity norm of this, so remember this is a function, you can bound by the operator norm of A times the trace norm of B, or the other way around. Okay, and you could also make P versions of this with that Schatten classes and so on, but let's not worry about this now. And what's also quite interesting is the following. So you see, sometimes, so in harmonic analysis, when you have a function that is not regular enough and you need more regularity, for example, you need more derivatives than you have, one thing you can always do is mollify. You can convolve with a very nice function to give the function more derivatives, and then you use some limit to get back your original function. And the same thing you can do here, not for all bounded linear operators, but just for the ones you would see as the replacement of bounded uniformly continuous functions. So that's the set that is continuous. Igor, you have a question?
Yes, Raffael. Please, this theory is already known, right?
Yes, this is known.
What text, what books do you recommend to study such things?
Well, the original results are due to Werner, and it's a paper from '84, but it's very compact and it's a physics paper, so it's maybe not so easy to read. But Robert Fulcher wrote a very nice paper about the Fock space. Maybe I can link it to you later.
Thank you very much. Thank you.
It's in Journal of Functional Analysis, yes?
Yes, exactly, yes. Okay, so this is, as I said, the replacement of bounded uniformly continuous functions is those operators for which this operation is continuous, and it's actually automatically uniformly continuous. Yeah, and for these continuous operators, you can do the same thing, mollifying. Let's say you can take some direct sequence, which just means a sequence of positive functions which integrate to one and which converge weakly to the delta distribution. Then you have that the convolution with these fn's converge in operator norm to A. And this is actually really nice because these operators usually behave much nicer than a generic operator A. It's the same as when you mollify in harmonic analysis. It's really the same principle. You get something nicer here. And with this, Robert Fulcher was actually able to prove just in a few lines that the Toeplitz algebra is linearly generated by Toeplitz operators, so that you don't actually need products in the definition of, or in the definition of the Toeplitz algebra. It's the same if you take the Toeplitz algebra, the algebra that is generated by the Toeplitz operators, or you just take Toeplitz operators and take the closure, and that's the same set. It's an original result of Xingbo Xia, and if you read Xia's paper, it's actually very long and very complicated, but with the help of this, Robert was able to show this just in a couple of lines, because he was able to approximate that very easily by these mollified versions, and then he was able to handle these really easily. So that's just a side remark. That's not the topic of today, but just to say this is also a very, very nice property. Okay, so now we understood convolutions a little bit, and now we want to have the other main player of harmonic analysis. That's the Fourier transform. And actually, we need the symplectic Fourier transform here, just because we're working on a symplectic phase space. If you're not too familiar with this, it doesn't really matter. It just has the same properties as the usual Fourier transform. So you have the symplectic form here instead of the inner product, but otherwise it's just the same. It has the same property. So it maps L1 to the functions that vanish at infinity, the continuous functions that vanish at infinity. And yeah, it also satisfies the usual properties you have for the Fourier transform. And now this is the operator version. Again, we just go more or less by analogy. So L1 is replaced by trace class. So we define the Fourier transform, or which is then called Fourier-Weil transform, or depending on who you ask, also Fourier-Wigner transform, which is nice that it starts with the same letter, so you can use FW either way. Well, anyway, so you do this, and then again, the integral you replace by the trace. You have your function, that's now an operator, and then you have these exponentials. Well, these are the characters, right, of your symplectic space, and these are then replaced by these while operators. So these now act as the characters of your theory. Okay, and again, well, you see here, because A is trace class, this is well defined. And now again, like for the convolution, the Fourier Wild transform has very similar properties as the Fourier transform. So you can now take this and extend it to a unitary map from the Hilbert-Schmidt operators to L2. And you can go further, just like you can with the Fourier transform when you do Fourier transforms for distributions. You can extend it to a weak star continuous map from the bounded linear operators into the tempered distributions. Okay, a weak star here refers to the duality trace class to bounded linear operators. So that's what I mean here by weak star continuous. So now you can take the Fourier Wild transform of arbitrary bounded linear operators in this way. And of course, what you want, otherwise all of this wouldn't make much sense, is the convolution theorem, right? You want, if you take the Fourier transform of a convolution, it should just be the product of the two Fourier transform. And this is indeed the case. This works out. You can prove this in both cases, right? Just here you need to make sure that you take the symplectic Fourier transform, otherwise the formulas don't work. But with the symplectic Fourier transform, everything works out. Okay, let's see an example again. Let's take our operator from before again and see what the Fourier transform of this operator is. Well, again, we can just plug it into the formula, the WZ here. We put it into the tensor product. We get W minus Z times the one function, that's K minus C. Well, then the trace of a rank 1 operator, that's the inner product. And of course, this inner product you can compute, that's an exponential. Okay, so the Fourier Wild transform of this operator is just the Gaussian. And now, whoops. Like this. Sorry. This now means that if you have a Toeplitz operator, because we know Toeplitz operator is F convolved with P, well, now we can use the convolution theorem if we want to compute the Fourier Wild transform of this. Well, we can just use the convolution theorem. We get the Fourier transform of this times the Fourier transform of this. This we just computed. This is the exponential, and so we get this the thing here, which, you know, if f is just a bounded function, this can be a distribution, right? So this doesn't have to be a function. This can very well be a tempered distribution. But like this, we know what the Fourier transform of a Toeplitz operator is. Okay, let's see what the Fourier transform of a Weil operator is. Of course, this time we cannot just plug it into this formula, because, well, this formula only works if you have a trace class operator, right? And for bounded linear operator, it was defined via duality, right? So we have to make a dual pairing with a trace class operator. Then the thing here makes sense. This Hilbert-Schmidt inner product makes sense. That's just a trace. So if B is trace class, this again makes sense. So that's the definition of the Hilbert-Schmidt inner product. That's the way how we dualize on the operator side. And well, this here is now by definition just the Fourier Wild transform of B, well, at minus psi. Okay, and you see on the other side you use that use an identity here that you also know for the usual Fourier transform that also works here to get this this here. And what this tells you now is, if you compare the left and the right-hand side, is that, well, all this Fourier transform of the Weil operator does, well, it evaluates at minus psi. And because this works for all trace class operators B, this just means that this has to be the delta distribution, right? Because it's just evaluation at minus psi, so this must be the delta distribution. It's maybe a little bit annoying that you have a minus here. Maybe it would be nicer if you have plus, but okay, that's just how it comes out of the theory. But again, it reflects that these while operators are really the characters of your theory, right? Because if you put in the characters into your Fourier transform, you get a delta, and the same happens here. If you put the while operators in, you get a delta. Well, you get delta minus psi, but well, anyway. Good. Okay, so this way we can actually compute all these Fourier transforms. Okay, and now we can come to the main theorem in this area in quantum harmonic analysis. It's due to Werner. Werner was the guy he's a physicist, and he invented this theory already in '84, but well, it didn't get much traction in mathematics. So only very recently it came up again, and it proved actually really useful to study function spaces and Fock spaces and so on. But what does it say? Well, it says, let's say we have a trace class operator on our Hilbert space such that the Fourier transform of it has no zeros. Okay, and then it says that for any closed shift invariant subspace of the bounded uniformly continuous functions, there is a unique closed shift invariant subspace of this replacement of the bounded uniformly continuous functions. I put it again up here. So as I said before, this is the operator version of BUC. And we can, and well, this space satisfies that an arbitrary operator in C1 is in D1 if and only if the convolution with the operator you started with at the top here is in D0, and also the other way around. So you have a one-to-one correspondence between closed shift invariant subspaces of this BUC and closed shift invariant subspaces of this on the operator side. So you have a one-to-one correspondence between function spaces and spaces of operators. And moreover, you can show that you can get always back and forth by convolving with all these trace class operators and take the operator norm closure. So with this convolution here, I mean just you take all the so this is a set, right? These are sets, and you take all operators from here, all operators from here, you take all the convolutions, and then take the closure of this set. And if you do that, you get exactly the zero. And if you, well, and you can also do it the other way around. So you can always switch from one to the other. And what's interesting here now is, maybe more interesting than the theorem itself, is the main example. This was actually also already known to Werner, that if you put in the functions that vanish at infinity, the corresponding space on the operator side are the compact operators. And I can show you a quick proof of this. Let's get into it, and then afterwards I will tell you what this actually means for our operators theory, for example, on the Fock space. So we need to prove that the compact operators can be written in this way, right? Because that's what we know from the theorem, that D1 is exactly this set. So if we want to show that D1 is actually the compact operators, we need to show this identity. And it's actually not too difficult. So we know that if we take just the functions that vanish at infinity and are continuous in L1, we know this is a dense set. Okay, and then we use Young's inequality to show that this set here is then dense in here, right? Because this is dense in here, and then if you convolve, this will translate. So this will be dense in this, and it will actually be dense in the trace norm. Okay, and then it's also not so difficult to see that this set is again just all trace class operators. So if you convolve all trace class operators with all L1 functions, well, you get all trace class operators. Okay, so this here is dense in the trace class operators with respect to the trace norm. And now we can just take the operator norm closure of this. What does it mean? Well, if you take the norm closure, the operator norm closure of the trace class operators, you get just the compact operators. And well, that means, here you get the operator norm closure of this here. And this, of course, is contained in this here. So the closure of this is contained in this. And so you get one direction. So the compact operators are in here. And the other way around is actually very similar, because, you know, this here, these continuous functions in L1 that vanish at infinity are also dense in C0 with respect to the supremum norm, right? And so with the same argument as before, this here will be dense in this here, right? You should take again Young inequality, and now it's dense with respect to the operator norm. And well, now you see, since this is contained in trace class, well, this means if you take now the closure, well, you get that this here is contained in the compact operators, because, well, trace class operators are all compact. So if we just take the closure here, you get that this here is contained in this here, and that's the other direction. So really, the corresponding space to the Z0 function is the space of compact operators. And what does it mean for our Fock space? Well, we get a very well-known result, namely, if you now take for A our projection onto the constants, right? We just computed the Fourier transform of it. We know it's an exponential, so this is fine because an exponential has no zeros. So if we put in here this projection we've seen, we know we can use the theorem with this A, and we also know convolving with A gives the Bayesian transform, right? That's what we computed before. So if we take for A this projection operator that I called P index Z, then what this tells you is an operator is in D1, which is now the compact operators, if and only if the Bayesian transform is in D0, where D0 is exactly Z0 in this case. So you get the result, an operator in here is compact if and only if its Bayesian transform is vanishes at infinity. Okay, and that's a result that is usually attributed to Bauer and Israelowitz. They proved that, well, for an operator in the Toeplitz algebra, this operator is compact if and only if the Bayesian transform vanishes at infinity. Now, that's almost the same result, and was almost already known by Werner. You have to work a little bit more to show that this is actually equal to the Toeplitz algebra. I didn't tell you yet, but one can show, again, with some quantum harmonic analysis techniques, it's actually, again, just a couple of lines, can show that this, in this case, for the Fock space, is actually just the Toeplitz algebra. So you really recovered the Bauer-Israelowitz theorem. And so this result was actually, well, at least almost already known in '84 by Werner, but, well, as I said, his theorems and his theory wasn't really, they weren't really recognized by mathematicians very much. And so, yeah, we could have had this much earlier if we knew about quantum harmonic analysis. Okay, so I think that's for now enough about quantum harmonic analysis. Let's jump into some applications to polyanalytic Fock spaces. So let me just quickly recall what they are. So now, instead of just taking analytic functions, we take polyanalytic functions. So those are the functions that for which the nth conjugate derivative vanishes instead of just the first conjugate derivative. So if you put n equals 1, you just take once. But now we take these functions. These are then called polyanalytic functions. And due to a theorem of Nicolai, there is actually a very nice decomposition of this polyanalytic space into what are called true polyanalytic Fock spaces, which are now denoted by F2 of index bracket J, and they can be written explicitly in this form, but this is not going to be very important later on, just to mention that. But what's important here is that this polyanalytic Fock space decomposes into these true polyanalytic spaces, and that's important for our analysis later on because, well, you remember we needed this irreducible representation, and as we will see, it will be irreducible on these true polyanalytic Fock spaces, but not on the whole one. So it would be reducible on this exactly. It would be reduced exactly by this decomposition. And so if you're interested in the full polyanalytic Fock space, well, afterwards you could just put it back together. Just prove everything on these smaller spaces first, and you could put everything together again. But so for now, because it works better with our theory, we just consider these true polyanalytic spaces for now. And they are just like the analytic Fock space. They are reproducing kernel Hilbert spaces. So you have an orthogonal projection that you can write down explicitly. You have reproducing kernels that you can normalize. They look actually very similar to the one on the analytic space, but you have an additional term here in front. That's a Laguerre polynomial. It's actually not so important what it really is. Excuse me. Just keep in mind it's a polynomial. All you need to know is it's a polynomial. If you know what Laguerre polynomials are, is fine, but that's actually not so important. But there's a polynomial times the same exponential as we had before. And, well, you can define Toeplitz operators the same way, really. So again, Toeplitz operator is multiplication with some bounded function f, and then using the orthogonal projection to get back onto your true polyanalytic Fock space. And just like for the analytic Fock space, you can write these Toeplitz operators as convolutions with some rank 1 operator. Now, the 1 functions have to be replaced by these normalized reproducing kernels, but where you put z equal to 0. Okay.
It's basically first basis element on the true poly-Fock space.
Yes, exactly. Yes. And the same thing for the Bayesian transform, right? You can form a Bayesian transform in the same way. And this will also be exactly the same computation. You have to write a little bit more because there is a little bit more in the functions. But by the exact same argument, you see that the Bayesian transform is also given by such a convolution, and you see the same rank 1 operator here again. So up to now, really everything is the same. And really, you also get this way an irreducible sigma representation of the symplectic space. Okay, so these are the Weil operators from before, exactly the same operators. They actually commute with the projections. So these polyanalytic Fock spaces here are invariant under these Weil operators here. So you can take the same ones and they form again an irreducible sigma representation. So that means we can apply our quantum harmonic analysis. That's really all we need to apply it. So let's look at the theorem. Okay, so that's the theorem. Let's try to apply it here. But soon we would realize, well, there's a problem because, well, in the first sentence, you see, we need to take a trace class operator so that the Fourier transform of it has no zeros. And before, what we put in there was this projection onto the constants, right? And we know there, we computed this, the Fourier transform of this was the exponential, so it had no zero, so that's fine. But here, we would need to take this one, right? Because when we want the Bayesian transform here, right? We would need to take for A, we would need to take this operator here. So this would have to have no zeros in order for this theorem to be for this theorem to be applicable. But then you realize, well, if you take the Fourier-Weyl transform of this, you don't just get the exponential, but you get a polynomial times the exponential. And that's bad because polynomials have zeros, right? So you actually cannot apply the theorem directly because, well, if you take for A this operator, well, you get an operator for which the Fourier transform has zero, so it's not applicable. It actually gets even worse because by another result of Werner from the same paper, actually, he showed that the following are equivalent. So again, think for A, just this operator here. Then he showed this is equivalent that this map here, and what is this map? Well, this map in this case would just be, well, F convolved with this, and we know this is Toeplitz operator. So the Toeplitz map, so F that is mapped to the Toeplitz operators is injective, and here you see this is the Bayesian transform. So what it says here is, since our operator does have zeros, it means both the Toeplitz quantization and the Bayesian transform are not injective in this case. So this is, in other words, on these spaces, there are symbols that produce non-zero symbols that produce the zero Toeplitz operator. And there are non-zero operators that produce the zero Bayesian transform, which is of course really bad if you want to characterize something in terms of the Bayesian transform, because one of the main properties, really of the most useful properties of the Bayesian transform is that it's injective, right? So you compute the Bayesian transform of something you don't know, and then you get something maybe you know, and then you know because it's injective, well, you know what your operator is. But if you don't have this, well, this is really bad. And you couldn't expect such a characterization of compact operators, for example, because, well, that's what I've just said, because you can actually give very explicit examples where the Bayesian transform is actually zero. And this will then show you that you actually cannot have such a characterization of compact operators in terms of the Bayesian transform, which is, this is just a counterexample. So let's check this counterexample. So what I want to show you is that if we take the Weyl operators and take this Bayesian transform, then we get actually zero. Well, if C is a complex number such that this polynomial is zero. So if this Z is the zero of this polynomial. Well, how do we do that? Again, we use our tools. We use the Fourier transform. So we show that the Fourier transform of this is actually zero, and then this shows that the function itself is zero. So what is the Bayesian transform? Well, we know we can write the Bayesian transform as a convolution, and then we can use the convolution theorem. We know what the Fourier transform of A is. Well, of this Weyl operator, we computed this. It was a delta. So we get delta minus C. Well, in the Fourier transform of this, we didn't compute. We computed it for the one function, but yeah, this is just this term when you get the Laguerre polynomial again. So just by the same computation, you get this term. And now you see why this is zero, right? Because we used exactly one of these z such that this polynomial is zero. So we evaluate at a point where this function is zero, so you just get identically zero no matter what you do. So indeed, the Bayesian transform of this operator is actually the zero function. Of course, you could also compute this explicitly, right? You could just take your Weyl operator, compute the Bayesian transform, and you get zero. That works too, but it's a little bit quicker if you use the Fourier transform. Yes.
Your sigma j is a finite set. Because
well-
Laguerre polynomial has finite number of zeros.
Yes, Laguerre polynomial, and every polynomial has a finite set of zeros, but you have mod z square here, so these will be circles, in fact.
Okay. Yeah,
But this
sure.
will be a collection of circles. Yes.
Collection of
Yes.
circles. Thanks.
Yes. And so we've just shown that the Bayesian transform of these Weil operators is 0, and in fact, this is everything. So this is in the kernel. You need some more harmonic analysis that I won't show you now, but in fact, this gets you everything. So if you take the weak closure of the span of all these, that's exactly the kernel of the Bayesian transform. So this is really all you can get, because well, it needs to be a weak star closure, a weak star closed Z, so it needs to be at least this, and then you can show with the harmonic analysis that this is actually everything. So we know exactly the kernel of the Bayesian transform.
Raffael, if you
Yes.
consider not a whole bunch of operator acting in a true Fock space, are just Toeplitz operator, what will
I will
result?
come to that. I will come to that. A little
Okay.
bit of patience. Yes. But first, I want to show you that we can also very explicitly construct functions that produce the zero Toeplitz operator, which is also very unusual. If you think, if you're working with Toeplitz operators, it's usually something you don't expect, but this is also the case here. So if you take a character and we'll do the same thing as before, well, to compute the Fourier transform of this, write it as a convolution. We know the Fourier transform of a character is a delta, and then the Fourier transform of this is again this. So again, if you take z in this zero set, then this again will give you 0. And since this Fourier transform is injective, this means that your Toeplitz operator has to be the zero Toeplitz operator. And just like before, this is actually everything. So with essentially the same argument that I didn't tell you before, you would need it again here. But again, this is everything. So the weak star closure of the span of these characters is the kernel of the Toeplitz map. So this is everything that produces a zero Toeplitz operator.
So the point is that these symbols are just oscillating functions.
Yes, yes. And now, so let's go back to this. Maybe we can still get something out of this. Well, what you can do, of course, is instead of taking this rank 1 operator, you can take one for which the Fourier transform has no zeros, right? This doesn't really help you with your Toeplitz operators because, well, you want to study Toeplitz operators, so you cannot just replace this. You would get a different operator. You could study different operators with this, but it helps you a little bit with the Bayesian transform. So you can use a different Bayesian transform, and this would then work. So, for example, instead of the normalized reproducing kernels, you can take these functions here. They look a bit similar. There's a different polynomial here in front. No, this is not the Laguerre polynomial, it's a different polynomial. But if you take this one, then, well, if you take, again, this simple rank 1 operator, compute the Fourier transform, you get again a Gaussian. And this will again have no zeros. So if you define a different Bayesian transform, right, like this, you replace the K's with the L's, you get a different type of function, which is, well, it's not the Bayesian transform, it's some other function. So let's say it's generalized Bayesian transform. Then you get again that the Fourier Weil transform does not have any zeros, and so you can apply the theorem, and so you get the same result again. So you get a characterization of compact operators, for example. So an operator is compact if and only if it's in this set of continuous operators, and this generalized Bayesian transform vanishes at infinity. And that's actually a result that's a little bit older. It's not from the paper with Forscher. I think I talked about this when I was in this seminar last year. But back then I didn't know why this was the case. So I proved this by other means. I didn't know why this was the case, why this works, why this generalized Bayesian transform works, but the usual one does not. But quantum harmonic analysis really shows you why this is the case, right? It's exactly because the Fourier transform has no zeros. That's why this works, and the other one doesn't, but because the other one has zeros. But it also tells you that this is quite arbitrary here. You could take something else that doesn't produce any zeros here, and you can produce your own Bayesian transform, and you could produce your own result. So this is not very special here. You could take something else and you could get a similar result. It just depends on your zeros of the Fourier transform. But the quantum harmonic analysis explains this really, really nicely, I think. The other thing you can do is, as Nikolai said, you don't take all operators, but you only take the Toeplitz operators. And now I claim the Bayesian transform is actually injective on this set. So it's not injective, as we've seen, that there are operators that produce the zero Bayesian transform. But if you just take the Toeplitz operators, it's injective again. And I can show you a very quick sketch of a proof. Again, I will hide the main argument, but I can show you again how this works with the Fourier transform and so on. So you take again the Fourier transform of this. Now you can write this as a convolution again. So you first have the Toeplitz operator that's convolved once, then you take the Bayesian transform, which is again convolution with the same thing. Apply the convolution theorem, you get the Fourier transform of f times, well, the other function twice. So that's the squared of the function you've always seen. So the Fourier transform of this here. And now, again, with the same harmonic analysis argument, you can compute the kernel of this. And the kernel is, again, a weak star closure of, well, the zeros of this thing, like the weak star closure of the span of the characters, where z is such that this thing is here is zero. So it's, again, the same argument from harmonic analysis. And, well, this is zero when the polynomial is zero, but now you see that's the same set that we had before, except we have a square here, right? We have a square here, but this, of course, doesn't matter for the zeros. So this is just the same set as before, right? If you have a square here or not, that doesn't matter. So it's the same set as before. And so we see that these kernels actually coincide. So this is zero, if and only if this is zero, right? Because we know the exact kernels of both maps. And, well, they are the same. And so this is zero if and only if this is zero. So this means on the image of the Toeplitz quantization, the Bayesian transform is actually injective. And furthermore, and I won't have time to actually show you the proof, but we were then able to also show the compactness characterization, just limited to the Toeplitz operator. So a Toeplitz operator is compact if and only if the Bayesian transform vanishes at infinity. So that's the result you would expect. It doesn't hold for all operators, but it still holds for the Toeplitz operators. Thank you very much.
Thank you, Raffael. Very, very interesting talk.
Thank you.
You give us a lot of information that it will take time to understand all of this. But really very interesting.
Yeah, as I said, there's a paper on the archive where everything is in there. You can look it up. If it was a little bit too quick now, you can just check all the details.
Okay, please, questions or comments?
Yes, well, thank you, Raffael, for your talk. I want to ask you about the way you see this the way you see this theory that you call quantum harmonic analysis. So I understand that this theory or this term arises from the work of Werner, right? From this
Yes.
paper that you mentioned.
Yes.
And it was recently, people are paying more attention to it, like I suppose you guys. But so my question is like, I mean, I don't really know how to formulate my question, but how do people look at this theory? Like, which kind of questions people are trying to answer using this theory? I mean, you talk about all this, but like thinking about physics, do people have something in mind?
Well, Werner is from quantum information theory, so he had some applications in quantum information theory, but I'm actually not too familiar with what this actually is. I think Fock, like also in physics, his theory wasn't really recognized very well. So I don't think it's actually a thing in physics anymore, but it came back to mathematics, as I said a few years ago, and now people are trying to study more or less everything that you know from harmonic analysis. So, for example, you have some. I'm not sure how familiar you are with all this, but like, for example, Wiener's Tauberian theorem, and you have a corresponding result on the operator side, and so on. And so really people are now looking, and it's not just my group with Robert, but they're like, I don't know, maybe 20, 30 people. We had a conference a couple of months ago where really a lot of people were interested in this, but people just trying to think about which harmonic analysis results can we transfer to the operator side, and what can we do with it? And people have found a lot of interesting stuff that can now be used in operator theory and proved some strong results.
Right. So according to what I mean, listening to your talk, I have the impression that the theory fits well to study these Fock spaces. And
Yes.
I suppose it might be also natural to study Bergman spaces.
That's one of, that's a very good question. It's one of the main questions. Can we also apply this to Bergman spaces? And it's a little bit difficult because the automorphism group on the disk, for example, is not commutative, and this actually makes a lot of problems. So like the translation group on the complex plane, or also Zn or so, that's commutative, but the automorphism group on the unit disk is not commutative, and this makes a lot of problems. And actually we don't really know how to do it in the non-commutative case yet. But that's one of the main problems we study right now, and we hope we can study Bergman spaces with this as well, because I think it has very strong tools to do so.
Okay. Well, that gives me a very good idea of how people are using this theory. So very useful. Thank you very much, Raffael.
You're welcome. Thank you.
Raffael, 2 observations. Am I right that one of the main interesting theme in this quantum harmonic analysis to find a pair of corresponding spaces?
Yes.
Well, and second observation, yes, in the unit disk it's not so good, but if you pass to upper half plane, then you have commutative group of translations.
That's actually very interesting. Yeah, I haven't thought about that. That's a very good idea. We should try that. Yes. Very good. Yeah. Very good idea.
So you may try.
Yes. I'll talk to Robert about this. Yeah. Very good idea. Thank you.
Okay. More observation or questions? No more. So, Raffael, thank you very much for your very nice presentation. And
You're welcome.
we will keep
I'm always happy to be here.
you will keep you in mind for further talks.
Of course. Thank you.
Yes, okay. So with respect to our seminar, next week we will have no seminar, and we will resume on the 1st of November by the talk of Jessica.
Okay.
So
No, damos aplauso, ¿no? A Rafael, Nikolai.
no, in German it should be like this.
Yeah,
Thank
it's
you.
knocking on the table in German, but
Thank you, Rafael.
it wasn't actually, yeah.
Yes.
Thank you.
Thank you, Raphael. Goodbye, and goodbye to all of you. See you.
Goodbye. Have a nice day.
Good night. Bye bye.
Bye-bye.
Thank you.
Bye-bye.